So in the last video, we talked about the hydrogenation of alkenes, and we're going to utilize this new reaction to kind of talk about a neato kind of sidebar feature about what these kind of reactions can tell us about organic transformations. So I'm going to give you a series of alkenes, and we're going to talk about how we can hydrogenate these molecules. So what we're going to do is we're going to take each one of these three alkenes, and we're going to perform hydrogenation of these alkenes. So H2 gas, and then we're going to use our catalyst, our palladium on carbon, and we're going to hydrogenate each of these alkenes. So I'm just going to copy paste, and what I'd like you to do is just pause the video and predict the products that you would get for each of these reactions. Okay, so now what we're going to find is after you hydrogenate each of these alkenes, the only thing that's really going to happen is you go from an alkene to an alkane. So this alkene is going to get converted from double to single, same thing for here, double to single, same thing for here, double to single. And really we're going to get a very, not really exciting result, is that we're just going to get this alkene or alkane, and this alkane on the very top is going to be the exact same product that you get for the top reaction, the middle reaction, and the bottom reaction. And so that's not too terribly exciting, although this is where it gets kind of cool, which is what you can do is you can do a heat experiment to see just how much heat is evolved from this reaction. What we're going to find is that we're going to measure, let's say we can measure delta H, and these units are in kcal per mole, so it's always important to have units. And what we're going to find is that these reactions are all going to be exothermic. They're all going to give off heat. So we can do our calculations, we can find that out. And so what's really cool about this is that we can talk about the starting material's energy versus the product's energy. And what we can do is we can just kind of draw an energy diagram and see. So these are our three different scenarios. And then if we think about the products of each of these reactions, since they're the same molecule, we can basically put them on the exact same position on the y-axis. So each one of these have the exact same position on the y-axis. So we're going to the same position here and here and here. So same position on the y-axis. And the only thing that's changing really is how much energy is lost. For reaction A, it loses 30, or it gives off 30, B gives off 28, and C gives off 27. So you can say if the final products all have the same energy, what must really be changing is the energy of the starting material. And so really, if the reaction A is giving off the most amount of energy, so it's giving off 30, versus C, which is not giving off nearly as much, that must mean that A has to be a bit higher on the y-axis to start off on. So A might be somewhere around here. The distance between the starting material and the product is going to be 30 kcals per mole, and then that means that the final product C, this is not giving off nearly as much energy, so the gap here has to be smaller. So let's just say maybe it's right here, and then that must mean somewhere in between. So this is giving off 28 kcals per mole of energy. What's really cool about this type of diagram is it gives us some information about just how much energy is stored in the original molecule. And in general, whenever you're looking at energy diagrams like this, what you can say is that the higher on the y-axis a molecule is, the more energetic it is. And if the more energetic the molecule is, you generally consider that molecule to be less stable the higher it is on the y-axis. What we're going to say here is we can draw a general comparison between this alkene to this alkene and this alkene. And what you can see is that if you think about the number of bonds that are non-hydrogen bonds that are attached to the alkene, for this example on the very far left, for the A example, we've got one direct non-hydrogen bond to the alkene, two non-hydrogen bonds that are attached directly to the alkene, and three non-hydrogen bonds that are attached to our alkene. And keep in mind our alkene is right here, so this is our alkene. One bond that's non-hydrogen, two bonds that are non-hydrogen, and 1, 2, 3 bonds that are non-hydrogen here. And so the general conclusion or the general trend that we can draw from this kind of data is that the more highly decorated your alkene becomes by non-hydrogen units, the more stable they become as well. And then here's one other trend that's kind of neat, which is we can take an alkene and we can draw two different versions of this alkene. So we can have this version of an alkene and we can have this version of an alkene. And one alkene is going to be a trans alkene, so this is your trans alkene, and this is your cis alkene. And so if you actually did the same kind of calorimetry experiment, what you'd find is that if you hydrogenated the alkene, the trans alkene actually gives off 27 kcals per mole. Your cis alkene gives off 28 kcals per mole. And you know that if you do the hydrogenation, you get the exact same molecule. In both cases, you get butane for both of these. And so if you get a butane here and a butane here, it's the same kind of idea that you get the same energy of the products. And then that must mean that the cis molecule gives off more energy, which means that this cis configuration has a lot more energy to begin with. So overall, if you had to compare trans versus cis alkenes, the cis alkenes are actually going to be less stable.